Hello everybody, my name is Narcissi Boy. I'm presenting the paper The Chubby Lock Service for Loosely Coupled Distributed Systems, written by Mike Burrows at Google in 2006. Chubby is a lock service for loosely coupled distributed systems, originally built to solve an engineering need at Google. It's reliable, it has high availability, and should be typically available to many clients inside of Google. And basically, Google wanted developers not to worry so much about consensus as their projects grew, and so they built a library to sit over top of their projects while they built. It's easy to understand, and it was not intended to be research, it was actually an engineering project. Why would Google need this in the mid-2000s? Just gonna go back to their head count. So when they started, they had 8 employees, and by 2006, they had 6,000 employees. For their code base, they use Perforce, which is now called Piper, which is a basically monolithic version control, but they needed something to handle distributed systems in their data warehouses and on-prem. So they created Chubby. This is a reminder of 2006. This is what Google looked like and some other things that were happening around that time to give you context. We also decided Pluto was not a planet in 2006. Chubby's main features is that it has a coarse locking design, think like a SharePoint checkout of a file, and it's implemented as a simple library, easy to use, and it uses sessions and keep alives like a lot of other systems we talk about in class, basically to keep a relationship open between the server and the client. It's also known for its strong naming architecture for files and directories, its async event delivery, which is similar to PubSub, and leverages caching. I like to focus on the lock design because it's what I knew the least about. I learned that a coarse grain lock is something that you can lock a whole directory or project or work area in a server where you need to work or sort something out for hours or days, or sometimes your consensus system needs to untangle itself or decide who's the leader, and you don't want everyone to not be able to see what's in there, but you don't want everyone to be able to write in there as well. This is a coarse grain lock. It's cooperative, so it doesn't block other people from looking inside of the resource, but it just doesn't let 2 people have 2 write locks for one resource. Lots of people can read, 1 person can write. It synchronizes itself with synchronizers, which are little state machines written in bytecode, tells you where locks have been and they're open or closed and who has them. Locks are advisory, not mandatory, so they only conflict with each other in that one case I mentioned above, and this was meant to help productivity, not hinder it. So it uses the Paxos consensus algorithm where there's a master leader and they all vote and poll and make sure that they're all up to date, just like we've learned in class. And it also uses caching, as I mentioned, and PubSub notifications. But most importantly, it uses a naming system that also doubles as its like node to node system. So like how to find everything. So this looks like over here on the right, LS looks like just like a path, but that actually means lock service. It means you are in somewhere maintained by Chubby. Foo is the name of that Chubby server who's handling something inside of the folder Wombat and inside of a folder pouch. So pretty intuitive. The system structure is really simple. It's just whatever software developer team's working on with the Chubby library imported into it, and that handles all the RPC calls to the assets in the data warehouse. And in the data warehouse, you can expect to have as many machines as Google had back then, but a single Chubby cell was 5 servers, and they all knew who they were, their replicates, and 1 master. So what's the mid-2000s use case for Chubby? The paper presents a scenario of 10,000 multiprocessor machines connected on LAN, high-speed Ethernet, and 1 Chubby cell, and you want to read from a Google asset or whatever. So here's a read request. And read is really simple. Chubby's going to do everything you'd expect an RPC system to do. It returns the path, access to the data, and a read mode lock. And you might be like, who cares if someone read something? Why does it need a lock? That'll come up in the next slide. But here are some events basically that could occur while you're reading. Your file content's modified, your child was modified, the master failed, etc. So the client sends heartbeats, basically like our other algorithms, and is like, hey, I'm still reading, don't close out on me. And that can be for as many readers as the system allows. The case for a write is also interesting. So a client has a write mode lock, so they're writing to something, and then someone also wants to read from that same file. They can do that, but when the writing is done, Chubby sends an event to the client and lets them know that some changes were made. And this is like pretty convenient, I would say, for back then if you're thinking about physical data warehousing and stuff like that. I'm going to kind of skip past failovers, but it's basically like all the other systems we've studied. Your master dies and they do a re-election and they figure themselves out. It's pretty much the same here. So Chubby today, after Java joined Google's code base, it was harder to adapt it to the library that they built, but it is still using Google file system, Bigtable, and MapReduce. It's heavily used as a naming server instead of DNS because it's so simple and intuitive. And it's blamed for 2.5 hours of cloud downtime in 2019. And I couldn't find much more about why, but it is blamed for some of that. Here's my references, and real quick, check out the author. So this guy's super smart, and he has like nothing on the internet about him. But if you look up some stuff, he's done a lot of things that really like build off of distributed systems in Google. So yeah, look him up, Mike Burrows, and that's it. Thank you.